let's take a look at an example so we can see how this particular one behaves. We have a mass of 1 kilogram, a spring constant of 6 newtons per meter, and a damping coefficient of 4 newtons per meter per meter. So that being said, an initial position of 1, a stretch of 1 from equilibrium, and a velocity of 0. So here I just copied and pasted the equation so that we would have it, computed the eigenvalues for this matrix. So this matrix is really just 0, 1, negative k over m, so negative 6 over 1 is just negative 6, negative b, which is 4 over 1 is negative 4. When we compute the eigenvalues and eigenvectors of that, we get negative 2 plus I times the square root of 2, negative 2 minus I times the square root of 2, and then the corresponding eigenvectors, which we said we don't really need because that's already built into the solution. So I'm going to just take a moment to identify everything. A, B, C, and D come from my original coefficient matrix. So A is 0, B is 1, C is negative 6, D is negative 4. And then for my G plus or minus HI, I see that G is negative 2, and H is the coefficient of I, which is square root of 2. And then, of course, what we want to compute is just so we can just plug everything all in one fell swoop. Negative A plus G over B. So that's going to be 0 plus negative 2 is negative 2 over 1 is negative 2. And then finally we could do negative H over B, which is going to be negative square root 2 over 1. So just square root 2. So H over B is just going to equal square root of 2. Okay, well that's all we need in order to build the solution, so let's go ahead and build this. Now let's remember that what's inside of this y vector at this moment is the position and the velocity. So the reason that is the case is because our equations are dy dt and dv dt, so what we'll solve for is position and velocity. Now it turns out that this second equation, velocity, is not going to be very useful in terms of graphing it. It's just going to really be the derivative of the y equation. So but we do need to use it so that we don't have to go back, and the beautiful part is with second order equations, we had to take the derivative of the position to get the velocity so that we could plug in our initial conditions. But here, it's already part of the vector. So it's really, really nice. It's a faster way to solve that kind of problem. Okay, so we're going to have yv equals k1 e to the gt, so g is negative 2, so we can see we're going to have an exponentially decaying amplitude. Makes sense. We have a damping coefficient of 4, multiplied by cosine of the square root 2t, and then we will have down here negative a plus g over b is negative 2 cosine of square root of 2t minus h over b, which we said was square root 2, so minus square root 2 times the sine of square root of 2t. And you can kind of see that the derivative of cosine of square root 2t is negative square root 2 sine square root 2t. The reason we get the extra term here is because it's actually a product rule thing that we would have to do, because we have e to the gt times cosine. So we would have to take this is basically going to end up being what we would get if we took the derivative. So the second term is going to be plus k2 e to the negative 2t times sine of square root of 2t. And then down here, same thing as the cosine function from the other half, negative 2 sine of square root of 2t, and then plus h over b. H over b was square root 2, so it's going to be plus square root 2 cosine. Let me back that up a little bit here. Plus cosine of the square root of 2 times t. There we go. And that closes that vector. So now we can write the y and v equation. So y is going to equal k1 e to the negative 2t cosine square root 2t plus k2 e to the negative 2t sine square root 2t. So let me take a moment and write that out. So k1 e to the negative 2t cosine of square root of 2t plus k2 e to the negative 2t sine of the square root of 2t. And then the second equation is going to be the uglier one. V equals k1 e to the negative 2t, negative 2 times that. And you can think about that negative 2 as being what happens when you take the derivative of e to the negative 2t. It's the chain rule. And this is cosine of the square root of 2t minus square root 2 k1 e to the negative 2t sine square root 2 of t. And same thing for the second term, but with the corresponding expressions. So this should be a minus 2 here, so let's go ahead and fix that. All right, so here we go. Minus 2 k2 e to the negative 2t sine of the square root of 2t plus k2 e to the negative 2t times cosine of the square root of 2t. Oh, we forgot a square root of 2 here. So let's go ahead and try that again. Okay, and there we have it. So next all we need to do is just go ahead and plug in our initial conditions. So we already have the initial position as 1 at time 0. The initial velocity at time 0 is 0. So if I do some substitutions in here, the position is 1. k1 e to the negative 2t, when t is 0, all the exponential pieces will be 1. So we'll just have 1 equals k1. Cosine of square root 2 of 0 is just going to be 1. Cosine of 0 is 1. So this will just equal k1. And then here, when we plug in 0 for sine, that's going to be 0. So this whole second term is going to go away. Well, nice. We've just solved for k1. V, the initial condition for v is 0. So if we plug in 0 for the sines, those are all going to be 0. So these two terms here will cancel out. And we'll only have the first and the last term, which will be negative 2k1. Again, e to the negative 2 times 0 is 1. Cosine of 0 is 1. And then the last term here will be plus the square root of 2k2. So now we can solve for k2. We already know what k1 is. k1 is 1. And so here we can do a quick substitution, probably faster than going to Wolfram alpha. And now we can solve this for k2, which is relatively quick. All we need to do is just add 2 to both sides and divide by the square root of 2. So we get k2 equals 2 over root 2. Now we don't need the velocity equation, so it's not like we need to deal with v again. This, remember, is just the derivative of y. So you can take the derivative of y and see that you get v as expected. All we really need is the position equation. So this guy here, we're just going to plug in k1 and k2, and we've got our solution. So y equals k1 e to the negative 2t cosine of square root of 2t plus 2 over square root 2 e to the negative 2t sine square root of 2t. And there we go. We have solved our spring mass system. And that's it for this video. We're done with complex eigenvalues. Next, we'll start to look at how does this apply to nonlinear equations.